I'd like to thank the organizer for the invitation. It's a great honor to be here. Also, it's great to see many old friends. So I will first talk about a little bit about classical Riemannian surface theory, and the goal is try to discretize these two-dimensional Riemannian surface theories. And it turns out there are many ways of doing it, and so I will focus on two in this lecture series. One comes from circle packing, the other one comes from vertex scaling. I will say more about it. So let me begin with a quick review of Riemann surfaces. And to fix the notation, I'm going to let S to be a connected orientable surface with no boundary. Okay, so it could be non-compact though. And so let me quickly recall the complex structure. A complex structure that's the basis of, I'm going to call collection C on the Riemann surface. This is a collection of charts. So it's a complex structure on the surface is a collection of charts. This is just a quick review of it. Satisfy two conditions. The first is that every point lies in one of the charts. And the second condition is that the transition functions are holomorphic. It's holomorphic. So we all know that. And being holomorphic means nothing but orientation preserving and angle preserving. And so this preserves angles. So with this pair, we call the surface with this special collection of a pair. This is a Riemann surface, and so the main ingredient that's going to be used is that we can define the angles. So in a Riemann surface, we can define what's the meaning of angles just using a chart. And so here you have a chart phi alpha, and then you have another chart phi beta. And suppose you have two smooth curves on your surface, and you want to intersecting at a point, you want to define the angle between the two. Just use this chart map to measure the angle in the Euclidean space, and this measurement is independent of the choice of the charts because it's a holomorphic. This is okay. So that's a classical theory of Riemann surfaces, and it's pretty universal, as we all know. The simplest example comes from really Gauss's study. So suppose we have the surface, and I have a Riemannian metric. So this is a Riemannian metric. And then, assuming we assume the surface is orientable, then that will automatically produce a Riemann surface structure on the surface. The naive thinking is because I have a Riemannian metric, and so I can use a metric to define the notion of angles. And what Gauss proved is that with any Riemannian metric on the surface, you take any point in your surface P, you can find a small neighborhood of that, and there is a map from the neighborhood to the complex plane preserving angles. And these are the so-called isothermal coordinate for the Riemannian metric, and you can take this phi, make them to be orientable, orientation preserving, and these are the charts. So we have many Riemann surfaces. In particular, if I have a surface embedded, this is a smooth embedded surface in three-dimensional space, like a human face, and that will make it a Riemann surface. Okay, and because of this notion of angles, and so here is one of the key concept which we will try to discretize it. It's a conformality. So suppose I have two Riemannian metric This is two metrics, Riemannian metrics on the surface, and they are conformal. Meaning they define the same notion of angles on the surface that from linear algebra we know they differ by a scaling of a positive function, okay, for some smooth function from the surface into R. Okay. So if you have two inner products which differ by a positive scaling, then they define the same notion of angle. So this is a conformality. And we can also define the underlying Riemann surface structure to be the equivalence class of Riemannian metric under this equivalence relation. Okay, so here comes the main theorem in Riemann, one of the main theorems in Riemann surface. This is the uniformization theorem by Poincaré. And Curb proved 100 years ago. The statement is this: I give you any surface, it's connected without any assumption on topology, it could be compact, non-compact, and I give you any Riemannian metric on the surface, and I have no assumption on the metric, it may not be complete, then you can find a conformal change. So then you can find a so-called conformal factor on the surface such that I can make a conformal change of the metric. So e to the 2u es squared. This metric is a complete metric, metric of constant curvature. Of constant curvature of Gaussian curvature, constant curvature K to be -1, 0, or 1. Okay, so that's, and furthermore, we can say that this U is almost always unique, and so U is unique if K equals -1 and U unique, unique up to scaling if K equals 0. Okay, if K equals 1, that's a spherical metric on an orientable surface, and so the surface is really unique. It's a two-sphere, and so in that case, we can make a Möbius transformation on the two-sphere, and so this U is not unique, but is unique up to Möbius transformations. So that's the uniformization theorem stated in terms of the conformal geometry of Riemannian metric. And this, by the way, because the uniqueness is so powerful, you only need to prove the theorem, just make a remark. Because we have these two uniqueness theorem here, you only need to prove it for simply connected ones. So only need to prove it for pi1 for simply connected surface. Because if the surface is not simply connected, you look at the universal cover and the pullback metric, and then apply the theorem for the universal cover. Because of the uniqueness, that will guarantee the same theorem. Okay, so that's because of the uniqueness, we can reduce the uniformization to simply connected surfaces. And one really simple consequence of this is the Riemann mapping theorem. So I take a simply connected domain, open connected set in the complex plane other than the whole plane, and I apply the standard Euclidean metric, restrict the Euclidean metric on the open set, and that fits into this profile. And according to the uniformization theorem, it has to be conformally the same as to the two-sphere, this is simply connected complex plane, the Euclidean plane, or D. And that's not the case because we have a non-compact surface. And this is not the case because of the Liouville theorem. And so it has to be conformal to the disk. And that's the Riemann mapping theorem. OK, so that's sort of the guide for us try to discretize, try to produce some kind of a, oops, it's too high. Yeah, where is the core? Oh, yes, got it. Thanks. Oops. OK, so what we are trying to do in a discrete setting. Well, the motivation for me was I was talking to my collaborators in computer science and graphics theories. And so we applied the uniformization theorem to my face, and then, which is a smooth, simply connected surface, it will be conformal to the unit disk. So it's a generalization Riemann mapping, which is not planar. So I really want to see how my face is conformally flattened to a disk. And I'll show you the picture. So we want to discretize it. So there are a couple of questions of guiding principles of how to do that. So the main question is whether there is a discrete version of the uniformization theorem for polyhedral surfaces. There are three guides that we need to guide us to do it. First of all, it has to be computable. So the theorem is just does not really produce any way to compute the conformal maps. And there should be, as a second, there should be a sort of a discrete version of the uniformization theorem. So discrete uniformization theorems that should be there. And the last thing is a convergence. So these discrete conformal maps should converge to the smooth conformal maps. Otherwise, it will be sort of irrelevant to the goal. And now there are many ways of doing it. And so here is two discrete versions of it, which has been done by a lot of people. And this is nowadays called sort of a structure-preserving discretization. And here is the principle which guides us to do it. And so we have a holomorphic map. It's a holomorphic diffeomorphism. And we try to see what is a discrete version of it. Well, a holomorphic map is the same thing as for every point, the derivative of this holomorphic map is a similarity linear transformation. So it's a rotation and then plus a scaling. So I'm going to call this. So we try to discretize those linear transformations which is obtained by scaling and rotation. And so what are the properties of those linear transformations geometrically? Well, it's the same thing as a linear transformation preserving circles. So if you have a linear transformation sending circles to circles, that will be something like this. And this is the corresponding discretization in the circle packing theory. Circle packing, really initiated by Bill Thurston. Well, I will talk a lot about it today. So I'm going to abbreviate as CP. Another way to describe a linear transformation, let's assume orientation preserving a linear transformation as a similarity map is the L preserves the length cross ratio. So it's really the cross ratio in a complex analysis, and you take the absolute value. So I'm gonna just draw the picture for you, without writing too many words. So you take a quadrilateral, and you apply the linear transformation, you get another quadrilateral. Now you compute the length. Say the length is A and A prime, and B prime, and here the corresponding length is X prime, Y and Y prime. Then these linear transformations are exactly the one which preserve the length cross ratio, which is AA prime, BB prime equals XX prime, Y prime. And so this is called the length cross ratio. And if we discretize this property, that will be the talks in tomorrow and the rest of the three talks. This is called the vertex scaling discretization. And so I will probably say more about it. There are still a lot more open problems in this setting, and the circle packing is really well developed. Okay, so that's just an overview. Let me now begin with an introduction of the subject. So these are the so-called polyhedral surfaces. I'm going to abbreviate as PL surfaces. These are the surfaces that appear a lot nowadays in digitization. So here I have again a surface which is connected on the orientable, say, and also I'm going to take V. This is sort of as a vertices. This is a discrete subset of S. Most of the time it will be a finite subset for compact surfaces, but I'm also going to talk about infinite case because we want a discrete uniformization for non-compact simply connected one. And so that will be the case. Now, so let me define a polyhedral metric kind of D on the surface with this very special collection of vertices singled is a flat cone metric with cone angles, with cone points inside. So V is basically captures the cone points, the singularities of this flat metric. And so the examples are like the boundary of a convex polytope in three-dimensional space, something like that. These are PL surfaces. I like to emphasize here is a canonical one, which will be our goal, canonical ones. And that's a goal, we haven't proved that yet, is this. You take the complex plane and take a discrete subset of it and look at the standard flat metric. So these will be really the one appears in the discrete uniformization. So we want to show every polyhedral surface. If you look at the universal cover of that, within the discrete conformal class, it looks like this. Or take the open unit disk, take a discrete subset of it. And the discrete set could be accumulating here. So these are the standard, sort of the guide that we are looking for by the end. Okay, right. So here is another standard way of producing PL metrics on a surface with a set of vertices single out. The way of doing it is just to take a triangulation. So take a triangulation. Take a triangulation T of this marked surface. I also want that the set of vertices of the triangulation to be exactly the vertices of this V is exactly the set of vertices. And now what we're going to do is to replace each triangle tau in F2. 2 stands for the set of all triangles in the triangle by a Euclidean one. A Euclidean triangle and glues them isometrically. So this is sort of another way of looking at the boundary of the tetrahedra, which is a polyhedral surface. And I'm going to take 4 triangles. That's because I have a triangulation, and glue these parallel edges by isometry. And so assuming the corresponding edges are the same, and that's a way to reconstruct the polyhedral metric. And it's flat. The metrics are going to be flat except as the vertices. And one advantage, not a V, it's a C with a set of discrete set that's specified as a set of vertices. Yes, it's flat. Yeah. These are all flat one. Okay, so the advantage of doing this is that we can now represent. So in this way, I produce a surface with a set of vertices, and this flat cone metric. This surface can now be represented by a more sort of combinatorial data. I have a surface, vertices, triangulation, and now I can code this this metric by the length. And so L is a way to assign every edge a positive number. This is the edge length. So we just assign every edge a positive number subject to a triangular inequality. So suppose I have a triangle with edges I, j, k in the triangulation, and then we assign edges 3 positive number subject to the conditions that E, the triangular inequality is satisfied. Then I can reconstruct the polyhedral metric and everything. So this is just one way of representing it, but this I think we think of this triangulation as some kind of coordinates to parameterize the polyhedral metric. And if your surface is compact, this is a finite set of data, and that can be coded by a computer easily. So that's that. The other thing which are relevant to the uniformization is the discrete curvature. So the discrete curvature, I'm going to call KD of a PL surface is the angle defect. So the curvature at every point other than the vertices are 0. It's a flat, and the vertices is equal to 2 pi minus the cone angle. So curvature equal to 0 means flat, and at the vertices of the convex polytope, the curvature is positive because the sum of the angles is going to be less than pi. And so convexity implies that. And so, okay. For the convexities, okay. So, so these are really simple object. Now, there is also a very simple theorem. It's much easier than the smooth case. It's Gauss-Bonnet. Namely, the sum of the discrete curvature is equal to 2 pi. So let's assume SVD is a closed PL surface, polyhedral surface, and then the sum of the discrete curvature is equal to 2 pi. So equals 2 pi times the Euler of the surface. Okay. And the proof is really simple. I'm going to go over it because I'm going to use the same method to prove Thurston theorem today. It's a sort of a standard technique. So let's produce a triangulation. So take T a triangulation. By that I mean this is a triangulation of this flat cone metric where every triangle is a Euclidean. Okay, triangulation. Take a triangulation of the surface. And now let's compute maybe right here. Let's compute the curvature using the triangulation. So the sum of the curvature is equal to, according to definition, 2 pi minus the cone angle at the vertex. And so this is, I'm going to write it in this way, alpha V. So alpha is an angle in the triangulation at the vertex V, sum of all angle. So that's nothing but the cone angle at the vertex. So this is the vertex. There could be a lot of a triangle comes in, look at alpha. And this can be written as a 2 pi times the number of vertices, and then sum over all. And what we're doing is really, I have a triangulated surface. And now I'm looking at all these angles, right? A group according to alpha. And so this is really all angles alpha. Is sum over all angles alpha on the surface. And for that, I can write it as 2 pi times the number of vertices. And now I'm going to group this angle according to the triangle. So you look at the triangle in the triangulation with 3 angles, alpha, beta, gamma. So I group them according to the triangles, these angle lies. And because these are Euclidean triangles, that's going to be equal to the number of triangles. I'm going to write F2 in the triangulation. And that we know is equal to 2 pi V minus number of edges plus the number of triangles. Because in a triangulation, the number of edges, twice the number of edges is equal to 3 times the number of triangles. That's a triangulation, and that's 2 pi times Euler. Okay, so that's a proof. So let me give you a couple of examples of polyhedral metric. And these are the circle packing metrics. So here is the class of circle packing metrics. This was proposed by Thurston in his work on the geometrization of 3-manifold. So I'm going to abbreviate as a CP. So the setup is we fix the triangulation. Fix the triangulation P of a surface. And now Now here is a very simple way to produce polyhedral metrics based on the triangulation. So let's also take a positive number, assign a positive number to every vertex, and that's it. So so these are called the radii function, radius function. There's no constraint on it. Assign every vertex a positive number, I will produce a polyhedral metric for you. So this will produce a length function on the triangulation. And the length is just naively, you take an edge with endpoints u and v, and the length of that is equal to the sum of the radii. And this will automatically satisfy the triangle inequality. And so then also you see the circle packings. And so this will say, so suppose you have a triangle, V1, V2, V3, and I have this radius R1, R2, R3 assigned at the three vertices. And what you do is now you draw three pairwise tangent circles, so radii R1, R2, R3, and then and you look at the triangle going through the centers of it. So so this is R1, R2, 3, and then the length is R1 plus R3. So the triangle inequality is automatic, and you also see the circle patterns. There is a circle around, and then that's the name, the circle packing. Okay, so from this we produce this is a PR metric. On the surface, and that's the circle packing metric. I will also, for simplicity, I'm going to use the curvature of the circle packing metric, which depends on the length now, depends only on the R. Okay, so these are the circle packing metrics. And so here is an example which I will use to illustrate Thurston's theorem, which is quite striking. So suppose your triangulation is the boundary of the tetrahedra, which is this is a triangulated two-sphere, and now I assigned 4 positive numbers as the vertices, and we produce a polyhedral metric. This is sometimes looks like you take 4 pairwise tangent ball, and then you look at the surface coming from the centers of this ball. So these are circle packed tetrahedra surface. Okay. Okay, so I will show you what Thurston's theorem says about this case in a minute. Now there is also another very nice class of examples of flat one, which I think is really fascinating class. This is a Doyle spiral circle packing. And there is open, this really is a discrete exponential map, and Doyle's conjecture is still open. So here is Doyle's spiral. I will show you the picture of it by the end of the talk. So you take the complex plane, and I'm going to take the standard hexagonal triangulation. So of the complex plane. And this is the triangulation where every edge has length 1. Okay, it's a topological, and so this is a degree 6 vertex degree 6 triangulation, infinite triangulation of the complex plane. The vertex set, I'm going to take that to be the standard lattice, e to the 2 pi I over 3z. So that's a standard lattice point. And now here is a Doyle's construction. It's really fascinating construction that he's going to produce a circle packing metric by assigning, think of the vertex is a group, is an additive group, right? Take any map from the additive group to the multiplicative group. This is a homomorphism, a group homomorphism. Take any group homomorphism from the lattice group to that. And explicitly, this says that if I take m plus m e 2 pi I over 3, this is going to be equal to a to the m, b to the m for some positive number. So I give you a parallel positive number, I can produce a unique group homomorphism. And the amazing fact is that this curvature is always equal to 0. That's Doyle's discovery. So this is a flat metric in a complex plane, but it's not complete if A is not equal to B. These are called the Doyle spiral. And so I will show you the picture. It's a really pretty picture. If A and B have different size, and then it's going to spiral. So this you can also Google just Google Doyle spiral. You see a lot of pictures. So this is a flat metric on the complex plane with no cone points. Well, it's all flat. And the conjecture is that these are all. So Doyle conjecture. If you have a circle packing metric on the hexagonal triangulation, is such that the curvature is equal to 0 for all v, then R is a group homomorphism. These are all of these. Okay, so maybe let me say one word how he discovered. This is a pretty cool. Yeah. This is a abelian group, right? This is a free abelian group on two generators. Oh, so this a group homomorphism. A group homomorphism is the same thing as you can find A and B such that. That's This is a multiplication group. So and the description is this all. And what happened? What happened in this case? How he discovered it was this: you look at the triangles coming from this group homomorphism. By the way, if the graduate student here, it's really good homework to just go back and check that at every vertex, what you see is that you have these three triangles that are going to be similar under this group homomorphism, and the similarity map will be something like alpha, beta, gamma, and alpha, beta, gamma. So the sum of these three angles is going to be pi. And that's how he discovered. Okay, so that's a Doyle spiral. And let me now show you what system proved. And the proof is really simple and super elegant. Let me. Basically, what system proved is that for these circle packing metrics, the curvature determines the metric. So maybe let me say one word before going to the details. And so you may ask, where is the discrete conformality here? What's in Thurston's mind is that if you have two such a metric, on the same triangulation. Okay. Suppose you assigned, with the same triangulation, you assign different sets of radii, and he considered these two polyhedral metric to be conformally, discrete conformally the same. Because the size of the radius is changing, but it's a circle to circle. And so that's a discrete version of the conformality. Okay, so here is the substance theorem. It's proved in Thurston's famous notes. And the proof that it's essentially there, and then the proof I'm going to present it to you is sort of a little simplification of it by Marden and Rodden. The Marden and Rodden, yeah. Okay, so here is a statement. Suppose I have two, suppose R and R tilde from V to R are two radius functions on a closed triangulated surface. For compact is okay, you can replace it. And let's assume that they have the same curvature, such that the curvature are the same. And we want to say something about the metrics. And of course, if the two metrics differ by scaling, so R tilde is 5 times R, all triangles are scaled by 5, the angle is not changing. And so, you can, we see they have the same curvature. And his theorem says that this is the only way to do it. Okay, so this is really a wonderful theorem. It's a rigidity that the curvature determines the metric after scaling. So you're going back to this circle-packed tetrahedra. What Thurston's theorem says is that for these circle-packed tetrahedra, if you find the four curvatures and the four vertices to be the same, which is pi, then it has to be regular. Okay, so let's prove it. And the proof is based on a very simple geometric observation. So this is a lemma in Thurston's notes. And I'm going to talk about a super version of it tomorrow, where you will see a variational principle underlying it. But Thurston's proof was the sort of the most naive geometric observation. It's very intuitive, and basically you can just see it. So, so let's let delta be a Euclidean triangle of edge lengths, Li equal to Rj plus Rk. So that's exactly this picture. Okay, and angles theta 1, theta 2, theta 3. So Ijk are going to be are distinct. So maybe I'm going to just draw a picture. Redraw the picture. And what Thurston observed is extremely naive and simple. So, so here you have three pairwise tangent circles. Let's fix Rj and Rk. I'm going to increase the radius of Ri. So we're going to make it a little bit bigger. And let's now take a look at what happened to the angles. And you see the angle, this top angle is going to be decreasing, and the two-side angle is going to be increasing. And that's Thurston's observation. So then partial theta I, partial Ri is going to be negative. This angle is decreasing, and 2, partial theta I, partial Rj is going to be positive. So tomorrow I'm going to tell you how to see a variational principle coming out of it by Davidier's work. And that really, I will give a second proof of this using variational principle, because this is one of the sort of the first and really fantastic rigidity theorems in the setting. Okay. The red circle, I'm going to increase, just increase to a larger number. I fix these two sides fixed and increase a little bit. And I produce a new triangle whose vertices are the centers. And what Thurston observed is if you do that, this angle is going to be decreasing and these two angles are going to be increasing. Okay, good. Okay, so let's prove it. I think let's prove Thurston's theorem just using this. As I mentioned, this proof is really modern Rodden's proof after he simplified Thurston's. Is more or less in Thurston's notes, but he sort of cleaned up a little bit. Okay, so let's normalize it. Let's assume after scaling, the total sum of the radii to be the same. And say they are different. After you normalize, suppose the two radii are different, and we're going to claim that then the curvature will be different. Okay. So if this happens, let's look at the set of all vertices I to be the vertices where the R radius is bigger than R tilde radius. And by the assumption, this is going to be non-empty because the total sum is the same. Okay. And let's look at the J to be the complement of that. So, so at the point J, the R radius is less than or equal to the other one. Okay, so the claim is, this is a really ingenious observation of Thurston. If you look at the sum of the curvature at I, they will be different. So look at the set of all vertices where the radius is bigger, it's going to be bigger. And with that, we have contradiction because we assume the curvatures to be the same. Okay, so how does he prove it? It's more or less this Gauss-Bonnet proof. So I'd like to show you. So let's look at the sum of all curvatures at these vertices where the radius is bigger. This, according to the same computation, it's 2 pi times the number of vertices in I, just like what we have before, right? It's always the vertices, the curvature is a 2 pi minus something, just take that out. And now you break the sum, the rest of the angle into 3 categories. So, so I'm going to write like this. This is a triangulation. Oh, my time is up. So I'm going to be a little bit quicker. I think my time is up. So what's the meaning of this? Well, well, these red dots here, these vertices are the one lies in the I vertices. And so these are all in I. This is in I. This is in I. The rest of the white one is 0. And using this lemma, since because I'm running out of time, you will see immediately this term is the same. That's pi, and these two terms are bigger. Okay, so this is same, and this is strictly bigger, alpha tilde, and this is also strictly bigger for the R tilde metric. And that is equal to the curvature. Okay, so I'll stop here.